Okay, good morning, everyone. Let's get started. So in the last lecture, we started to talk about our first linear classifier algorithm, which is called perceptron. The perceptron has a long history, but it is like very simple, intuitive approach. So let us first review the algorithm steps of perceptron algorithm, right? So it is an online algorithm, meaning that I'm gonna keep processing pairs of the instances and labels. Then I update my model when I make mistakes, right? So specifically, let us assume we're gonna handle a sequence of training examples, x1, y1, x2, y2, and so on, right? And here we only consider about binary classification problem. So the label is either -1 or 1. So initially, we're gonna initialize our weight vector as 0. Remember, this is a linear model, right? So the model is determined by the feature weights and the Boss parameter, right? So we initialize our model parameters as 0. Then we sequentially process every example, x, I, y. I use my current model parameters to make a prediction for xi, right? And then check if my prediction is correct or not. If my prediction has already correctly classified the current example, now I'm gonna pass the current example and move to the next. Otherwise, I'm gonna update my model. So that's why it's called mistake driven, right? So I only update my model when I made a mistake to classify the current example. So the updating follows this rule. So I'm gonna add this product between yi and xi. Remember, yi is either 1 or -1 times some kind of small constant learning rate, r. We add this product to wt so as to get wt plus 1. Okay? So get our new version of the weight vector, we denote as wt plus 1, then we'll proceed to the next example. So keep processing every example, and every time we first classify this label, right? And then check if we can correctly classify that example. If I can do it correctly, I'm gonna pass this example and then proceed to the next example. Otherwise, I'm gonna use this rule to update our model, right? So like several important points about this algorithm is as follows, right? So first, if we look into this updating rule, we found that if we make mistakes on positive examples, you're gonna add WT, this R, learning rate R, times the example XI. If you make mistakes on negative examples, you actually subtract WT from learning rate R multiplying XI. So see that there's a little bit difference here, right? So if you do the positive, if you make mistakes in predicting a positive example, you're gonna add the input instance or input feature vector to your weight vector. Otherwise, you're gonna subtract your current weight vector by the feature vector. Right? And in most versions of the perceptron algorithm, the learning rate is simply set to 1. Right? And this whole algorithm is kind of mistake driven. It's a lazy learner in that I only update my model when I make mistakes. Otherwise, I don't make any mistake. Otherwise, I don't update my model. So we'll also talk about another trick to verify if you are making a mistake. Right? So we can just look at if this product is less than 0. And this product is the ground truth label multiplying with your score, right? Your classification score, which is the dot product between the weight vector and xi. Right? So why is this the case? We talked about before, right? when you make a mistake, no matter it is positive or negative, your sign of your classification score is always opposite to the ground truth label, right? That's why you multiply them together, you always have negative. Does it make sense? Right? Everyone comfortable? It's just a quick review what we have discussed last Thursday. Yeah. Okay. So that means like during our implementation, we actually do not need to directly predict label. We just check this inequality, right? If this inequality holds, that means, okay, you have made a mistake. You need to use this rule to update your model. Otherwise, you can you can proceed with the next training example, right? Okay. So then we'll talk about the intuition behind the update, right? So why should we follow the rule of updates, right? And what's the rationale, right? So we use this positive example as we use the mistakes on positive examples to illustrate the rationality, right? So if we made a mistake on positive example, that means the ground truth label is 1. And because you're making a mistake, that basically means your classification is a negative example, right? So that means your score must be less than 0. Right? Then if we follow this rule for the update, we're going to add xi to the current weight vector to get wt plus 1, right? So, and now if we check the score of wt plus 1 in classifying this same example, right? So basically we want to calculate the dot product between wt plus 1 and x, right? And you just substitute these updates for wt plus 1, you will get this one, right? So you see that after you update the model, your prediction score actually increases by x transpose x. And x transpose x is always non-negative, right? Does it make sense? Right? So that means like, okay, after you update your model, and then if you apply updated model on the same example, right, you'll find that your prediction score increases. That exhibits the rationality, right? Why? Because previously you made a mistake, right? You use your WT to classify this example, you make a mistake. The reason of the mistake is that your classification score is too small, right? It's below 0. So you predict it as a negative example, but the ground truth is positive example, right? So to save this mistake, right, to correct this mistake, you must make sure that after your model update, your score increases, right? We hope that your score increase will make your new will increase to be above 0. Then you can make the correct prediction, right? So that explains why we should update our weight vector in this way. Does it make sense? So we highly recommend you to write down this updating rule and check why doing this is reasonable. Any questions so far? Everyone is comfortable? Okay, let's just practice a little bit more. Let us consider in the case we have made a mistake on the active example. Right? And that means we're gonna use this rule to update our model, right? Let's see why this is the right rule, right? Why doing this makes sense, right? So if your ground truth label is negative and you make a mistake, that means like your prediction score will be it's bigger than 0, right? It's above 0. Then we can see that, okay, currently your model is kind of like a over prediction, right? And your score is too big. Then if you want to improve your model on predicting this example, you should decrease the score, right? And ideally, we expect that you can decrease your score to be below 0. Then you can correctly classify this negative example, right? So let's see. We follow the rule, right? Perceptrons update rule. In a negative case, it should be like this, right? So that means your new weight is got by subtracting WT by X, right? Here, right? So for clarity, I'm gonna spell it out, right? So this is your new weight, right? New weight vector actually is equal to subtracting WT by X. Then let's check for this updated model, what is the prediction score on the same example, right? So again, we're gonna check what is dot product between WT plus 1 and X, right? So we know that WT plus 1 now is WT subtracted by X, right? So we're gonna just replace, plus sign here by minus sign, right? Again, you do some expansion, you know that now your updated model will be equal to the score before the update subtracted by X transpose X, right? So again, X transpose X is positive. So you subtract by a positive number, you kind of decrease your score, right? You actually decrease your score. So now if we contrast to the scenario of our mistake, you will find this is reasonable, right? Because you're making a mistake on negative example, that implies that your prediction score is too big, right? It's above 0, right? It's above 0, right? This is where your prediction score, right? And now through your update, you subtract your score by some positive number, you kind of like decrease your score. You pull it toward below 0, right? Although it's not guaranteed to be really below 0, but at least your update is toward the right direction. Okay? That's the rationale of this update on the mistake on the case on a negative example. It's not necessary. You don't need to change the learning rate as well. So we're gonna discuss about some kind of theory about the perceptron update. It turns out that as long as your data is linearly separable, you just run this, right? No matter which learning rate you set, as long as it's positive, a small positive number, it always converts to a separating hyperplane, meaning that it's gonna correctly classify every example in your data set. Another question? Okay, so now let us look at this update in a more intuitive way. Right? We're gonna look at the geometry of a perceptron update. So suppose this is our classification boundary, right? And remember, classification boundary is orthogonal to the weight vector. So this is our old weight vector before we say a new example. Right? So now a positive example appears, and it shows up to be here, right? And so now I want to ask: is the current perception correctly classifying this example? No. Why? Yeah. If you check out the the score, right? Remember, the score is W dot product between W and X, right? So basically, whether it's positive or negative is reflected by the angle between the two vectors, right? If this angle is bigger than 90 degrees, that means, okay, it's negative. Right? Of course, this is bigger than 90 degrees. So that means like our current perception will misclassify this example into negative, right? Does it make sense? Right? And then let us apply the rule here, right? This is the case we make a mistake on positive, right? So we're gonna update our perception by adding current with vector W by this X, right? So that means we're gonna do this guy, right? And let us consider like how do we do vector addition? Everybody knows that, right? Everybody understand that. So we just move the vector in parallel to make sure that the head and the tail meets together, right? And then you draw then you connect the new head and new tail, right? So that's how we do that, how we do the vector addition geometrically, right? So you move X in parallel such that the tail of X meets the head of W, right? Now you just draw the new head and the tail, right? So now you got your new weight vector, and obviously your classification boundary is perpendicular to the new weight vector, so kind of change the direction of your change the position of your classification boundary, right? So now under this new weight vector, how is the classification on the same example? Does it correctly classify the example now? Yes, right? So if you look at, this is W new, right? And this is the input, right? So if you look at their angle, it is less than 90 degrees, so their dot product must be positive. So that means, okay, my classifier, my perception will give a positive prediction for this example, which is the same as the ground truth. So now we can see that, okay, after this update, we can correct our mistake. Any question? Okay, so let us look at another example for which we made a mistake on negative, right? So again, this is our current perception model, right? So the boundary and the weight vector. Now we say a new example, X, which is negative, right? So obviously we made a mistake on this. Why? Why our current perception will make a mistake in predicting X? Yeah, it's positive, right? So if you look at the dot product between this W and X, right? You see they must be bigger than 0, right? Why? Because their angle is less than 90 degrees, right? So that means, okay, my W will classify X as a positive instance, right? But it happens to be a negative instance. We made a mistake. Then, following the rule of the perception update, right? We're gonna subtract W by the current X to update our W, right? So let's see, after this subtraction, where will our new classifier boundary will be, right? So this is our W, right? When we subtract X, it means that we add a negative X. And negative X means that, okay, I'm gonna just reverse the direction, right? And then I move reverse the direction of the vector in parallel such that the arrow will meet the beginning, right? And then you just connect them. You get the new weight vector, which is dashed line here, right? And correspondingly, you got a new classification boundary. Right? So now, under this new weight vector, what is our classification results on X? Anyone? Negative, why? It's less than 0, right? Right. If you look at W nu transpose X, right? Dot product with X, it must be negative, right? Because their angle is is bigger than half pi or 90 degree, right? So it's negative. So now you correctly classify the label, right? You correctly classify the instance as negative, right? So you may you kind of save your mistake. Okay. So hopefully this like our analytical analysis and also like geometry interpretation of this update will strengthen your sense, like feeling, okay, this update is really reasonable. Any questions so far? Okay. So now we want to take a look at how powerful it is perceptual learning algorithm, right? So is there any limitation? So first, perception obviously cannot learn what it cannot represent. Right? So perception essentially is a linear classifier, right? So basically means like any class of functions which are not linearly separable won't be learnable by perception. Is there any such type of functions? We discussed this before, right? Which is what type of what instances of a function class that cannot be learned by a linear classifier or represented by a linear classifier. Even for Boolean function, it's not every Boolean function can be represented by a linear classifier, right? Yeah, if you could remember, we give a most simplest example is XOR function. Right? XOR function is not it's not. If you look at XOR function, it's something like this, right? This is where the positive instance, negative instances are distributed in this space, right? In this instance space. In this case, you won't be able to find any line that can well separate both positive examples from both negative examples, right? So Minsky and Papert, these two pioneers in artificial intelligence, in 1969, they wrote an influential book and showing that perception's representation is very limited. Right? The one example they show in their book is this XOR function. So it's not learnable. If you present XOR function to perception, you won't be able to learn a good classifier for that because it's not able to represent XOR function. Of course, there are many other instances for which a simple perception or linear classifier cannot learn. However, with the development or with the progress of machine learning, people have already found ways to work around it, right? The trick is called feature transformation. Right? We mentioned that before, right? So now that in the original space, these four instances, you won't be able to find any linear classifier to separate them, right? But then let us do some smart trick, right? Let us augment features and to lift up the dimensionality to represent each instance. Maybe in the higher dimensional space, you can easily find a hyperplane or classification or a linear boundary, which can well separate those positive and negative examples, right? Does it make sense? Any questions? Yeah, feel free to interrupt me if you feel uncomfortable or question any points we discussed in the class, right? Okay. So next, let us talk about the mistake bound of perception. this is about like some theoretical guarantees about perception, and this is the only theory you want to learn throughout this throughout our throughout this semester, right? So this perception mystic bound tells us two cases. One is that if your data is linearly separable, and whether your perception algorithm will converge, because this is kind of like a very intuitive question, right? You're doing this such a simple and lazy update, right? If you keep updating, will that enter into some like repeated cycles, or it will converge, meaning that it won't update for any example. And second thing is that, okay, what if your data set is not linearly separable, right? And then you just run your perception algorithm, what will happen? Okay, now let's first talk about the convergence theorem. So the convergence theorem tells us if your data set is linearly separable, meaning there exists a set of weights, right, that are consistent with the data, right? Then the perception algorithm will eventually converge. By converge, it means that it won't update for any example. It will correctly classify every example, and you don't need to update anymore. You can just quit, right? So that's good, right? At least it means that, okay, if your data is good, is as consistent with our assumption, and then your perception guaranteed to converge, it won't like update it for ever and ever. And the second theorem is called cycling theorem. It applies in the case that your data is not linearly separable, like X4, or many other cases where you can not really find out a linear classifier which will separate positive and negative examples. Then your perception will enter into infinite loop. So the learning algorithm will eventually repeat the same set of weights and keep doing this. So it will never converge because there's always some example misclassified by the model, and then you have to update. That means you're gonna switch to an existing state, and then you're gonna make some mistake, and then you're gonna update the model to a next state, and finally you'll see that, okay, you're gonna be trapped into a cycling of these states forever and ever. So this is called cycling theorem. These two theorems kind of like characterize the behavior of perception algorithm in other cases. Any question? Okay, so now we'll mainly talk about the first behavior, like convergence behavior. Right? Under this convergence behavior, we would like to know, okay, how many mistakes or how many updates will you need during the running of perception? So to talk about the results, right, we need to first introduce a very important concept called margin. So let us consider a linearly separable data set. As drawn here, we have a bunch of positive examples, we have a bunch of negative examples, right? So you are given a hyperplane or line, which perfectly separate all the positive examples from negative examples. So, and associated with this hyperplane is a metric called margin. So margin is the distance between the nearest point in this data set and your separating hyperplane. So let me repeat, right? It's the distance between the nearest point in this data set and this hyperplane. So in this data set, the nearest point obviously is this guy, right? Is this positive example, which is closest to this hyperplane. Then the distance between this guy and the hyperplane is called margin with respect to this hyperplane. Any question? This is definition. Any confusion about this definition? So basically, if you want to look at the margin of a hyperplane that separates a data set, right? You just calculate distance between every point in this data set and this hyperplane, you find out the minimum one, and that is your margin. And then we want to generalize this, we want to extend the definition of margin to be a margin for a particular data set. Again, this is for linearly separable data sets only. So we define a margin of a linearly separable data by as the maximum margin possible for that data set using any separating hyperplane. So if we look at, again, this data set, right? So see, this data set can be separated by infinitely many lines, right? And then we're gonna find out among all those separating lines, separating hyperplanes, which separating hyperplane gives you the largest margin. And that margin is defined as the margin of the whole data set. That's the definition of a margin for a data set. Any question? So this concept is extremely important because we're going to leverage that to introduce the computational learning theory, and which motivates the support back machines and VC dimensions, all kind of stuff. Okay, so if we look at the definition of margin for data set, you can see that this margin reflects how separable the data set is, right? So imagine like you kind of like, if you have a bunch of positive examples, negative examples, they're close to each other. The margin of this data set will be much smaller than another data set where the positive and negative examples are far apart, right? So this margin actually is a quantitative metric which measures how far away the positive examples from negative examples in your data set. Right? And then you can imagine like the larger margin a data set has, the easier for you to find out a separating hyperplane, right? I mean, you can easily find out a line, a linear classifier that will separate out positive and negative examples, right? However, if your data set has very small margin, like this guy, right? Sorry. Let me draw another set, right? So you see that in this example, the negative and positive examples are close, right? So the margin for the whole data set is small. Then in this case, it will be much more challenging to find out the separating hyperplane. So actually, the margin for a data set indicates the kind of like easiness and the separability of the data set and easiness for you to find out a linear classifier for that data set, right? Any question? Okay, so the last point regarding the definition of margin is this is only defined for separable data set and separated hyperplanes. If your data set is not linearly separable, it doesn't have any margin. Yeah, for this transform data set, you have margin, right? But for the original data set, which is not linearly separable, it doesn't have margin. Margin is only defined for separable data sets and the separating hyperplanes. Other question? Okay, just keep in mind, this is very important concept. We're gonna repeatedly use that again and again. Okay, so now that the margin is, according to the margin, right? Definition of margin, we know that margin is kind of like minimum distance between the data points and the hyperplane, right? So now we need to review how do we compute the distance between any data points and separating hyperplane H. So that means like we need to review some kind of like a knowledge we discussed, we learned in grade 8 or grade 7 or grade 10. I forgot, but anyway, I believe everyone has seen this during your junior school or high school, right? So in general, if I have a hyperplane, which is represented by this linear equation, W transpose X plus B equals to 0, then the distance between any point x0 and h is computed following this formula. Right? So basically, you can imagine you have some like high-dimensional space, you have a hyperplane, and in this high-dimensional space, you got a point x0. Remember, x0 is both point and a vector, right? And then if you want to calculate the distance between x0 and this hyperplane, sorry. You just follow this formula. Right? You just substitute x for x0. You just substitute x0 for x into this equation, and then divided by the norm of the weight vector. We got distance. Okay? And I encourage you to analytically show this is correct. Right? It's not hard, but it's a good review. So if we do this in augmented feature space, meaning that we're going to append a constant feature 1 to x0. Remember, this relates to our notation simplification trick, right? We want to fold our bias parameter into our weight vector, right, to get our new weight vector. So this is our new weight vector. And correspondingly, you're going to append a constant feature 1 to our original feature vector. We got a new feature vector. So that means actually you kind of extend your instance space, the dimensional space, right? And in this new space, you're going to calculate distance in this way. Okay? And again, because in this space, W includes everything, right? The weight vector and the bias parameter, and x0 is augmented by 1, right? So then your equation that represents the hyperplane is W transpose X equals to 0, right? And following the same formula, this is how you compute the distance between x0 and your hyperplane in the augmented feature space. Does it make sense? And suppose your weight vector or your hyperplane can correctly classify your example, x0. Then this absolute value can simply be written as y0 W transpose x0. Why? Mm-hmm. Yes, exactly, right? So here we are assuming, okay, because we're talking about margin, right? Margin means that, okay, this data set is well separated by your hyperplane. That means your hyperplane can correctly classify every example, right? So if you look at any example, the distance between that example and hyperplane, it is follow this calculation, right? But meanwhile, we know that, okay, that hyperplane can correctly classify the label for x0. So this product must be positive, right? Remember, y0 is either 1 or -1, right? If I make a correct prediction, your sign of your score W transpose x0 will be the same, right? So the product must be positive. So you don't need to really use this absolute value. You just express it as y0 times W transpose x0. And then you divide it by the norm of W. We got the distance. Does it make sense? Everyone feels comfortable? Yeah, if you don't feel comfortable, you just spend some minutes to look at this formula and just do some kind of calculation. That will be straightforward. Okay, so now let us talk about this theorem. It's called Mystic-Bound theorem. Where is this annoying stuff? Okay. So here's the Mystic-Bound theorem. let us assume we have m training examples, x1, y1, x2, y2 to xm, ym. And for every training example I, the feature vector is n-dimensional. And the norm of the feature vectors are upper bounded by some value r. This is reasonable, right? Because in practice, you won't have any value, any feature value to be infinite, right? It always have finite value for every feature. So that means your norm of every possible feature vector must be bounded, right? Let us just assume, okay, their upper bound is r. And the label is either -1 or 1. And suppose this data is linearly separable, meaning that there exists a unit vector. Unit vector means their norm is 1, such that there is some gamma, positive gamma. So we have for every training example, this yi times u transpose xi is no less than gamma. So what does it mean? Yeah, let's just put that. Let's go back to it later, right? And given these two conditions, right? Then you run a perceptron algorithm, no matter in what order you pass the sequence of training examples, right? The perceptron algorithm will make at most r over gamma square mistakes on the training sequence. So remember, r is the bound, upper bound of the norm of each training input vector, and gamma is given by the second condition. So basically, we assume that, okay, there is a separating hyperplane, but its norm of the weight vector is 1. And for every training example, it has a lower bound, gamma, for this product yi, u transpose xi. And then we assert that you run a perceptron algorithm, no matter what kind of sequences you can pass them into your perceptron training procedure, the mistakes the perceptron algorithm will make is at most this many. And then the perceptron algorithm will converge. That means it will correctly classify every example. Any question regarding what this theorem is telling about? Okay, so some kind of like notes about this theorem. So first, this theorem is based on assumption that, okay, we're doing this in an augmented feature space, meaning that every feature vector is augmented with constant 1, so that our weight vector has already included the boss parameter. And as we just mentioned, right, we can always make such assumption because every feature in practice cannot be infinite. So that means the norm of a feature vector, in other sense, you can view it as the length of a feature vector, will always be finite. So we'll have some upper bound R. The most important insight is about second condition. So if we take a look at the second condition again, we say if there exists a unit vector u, right, such that for every training example, yi u transpose xi is no less than gamma. So what does the left-hand side mean? What's the meaning of the left-hand side in this inequality? Yeah, if we can trace back to what we have just reviewed, the definition of distance, right? So because we're doing everything in augmented feature space, this is how we calculate distance between your data point and the hyperplane, right? So if your W is a unit vector, so that basically means the norm of your weight vector is 1, right? Then your distance is simply W transpose x0, right? And if your W can correctly classify x0, this guy is simply y0 W transpose x0, right? So now going back to look at this condition, right? So this essentially is the distance between xi and u and hyperplane determined by u, right? Remember, the norm of u is 1, so distance should be this product divided by the norm of u, right? But now we're assuming, okay, this is a kind of unit vector, so the norm of u is 1. It's just, you can just ignore it. Yeah, there's some point we want to emphasize right now. Okay, that's very good point. So that means for every training example, the distance between that example and the hyperplane determined by u is no less than gamma. So gamma actually represents the margin of this separating hyperplane determined by u, right? Does it make sense? So basically the second condition is assuming that you have a separating hyperplane which has a margin gamma. That's what the second condition means. Any question? Okay, so let me repeat it again because this is this is really important, right? So from the definition, from the definition of the second condition, right? So you see that for any training example xi, yi, you have this guy, this inequality holds. So left-hand side actually represents the distance between xi and the hyperplane determined by u, right? So this is u, right? This is xi. Why this is represent distance? Because u is a unit vector. If you just follow the formula to calculate distance, it is the distance. And it requires that for every example, the distance between that example and u is no less than gamma. So that basically means that the nearest point, distance between the nearest point and the hyperplane is gamma, right? So that implies, okay, this separating hyperplane should have a margin gamma, right? So overall, that means, okay, we're assuming this data set is linearly separable and there exists a hyperplane whose margin is gamma. And this hyperplane can be represented by this unit vector u. Someone may ask, okay, why should I assume there must be a unit vector, right? Why didn't I just assume it's just a vector and this has a margin gamma? Of course you can do that. There's no issue you can do that. But if you do this, you're gonna have a little bit more complicated bound, which you have to account for the norm of u. And that's it. And here we assume u has a zero, has a norm 1. It's just for simplicity. Okay? You're gonna leverage the same proof procedure to get a different bound if you just don't assume a unit vector. And actually, because any vector, any weight vector, you can divide it by its norm, you got unit vector, it doesn't change the hyperplane at all, right? So there's nothing influence on our conclusion. Yes. Yeah. That's exactly how this is derived. If you're assuming the norm of u is not 1, so that means, okay, you're gonna assume the distance. You're gonna directly write down the distance here, right? Right. You divide both sides by u. You got your gamma over u, right? And then you throw it into the same procedure. You're gonna get to the bound, but the new bound will be will be like this. You have to multiply the norm of u in your bound. Okay, any other question? Okay. A more succinct or plain language to explain what does this mistake bound theorem is. Suppose we have a binary classification data set with n-dimensional inputs. If the data is linearly separable, then the perceptual algorithm will find a separating hyperplane after making a finite number of mistakes. This is what this this is a message. This is a takeaway the mystic bound theorem delivers. Of course, more than that, the mystic bound theorem gives you some quantified bound. Okay, any question regarding the understanding of this theorem before we proceed to the proof? Okay, so now let us look at how do we show this, right? So here's our setting, right? We're gonna leverage this basic conditions and setting to show the mystic bound theorem. Right? So our setting includes the following. So first, initially we're gonna set the weight vector to be all zero, and then for simplicity, we just assume the learning rate is 1. Of course, you can have a more general version for arbitrary learning rate R, but here we just omit it for simplicity. Right? And all training examples are contained in a ball of size R. That's basically what this means, right? The norm of each input feature vector is R bounded by R. And also we have a separating hyperplane represented by a unit vector U, and with margin gamma, basically means for every training example, this yi, U transpose xi is no less than gamma. Okay. Now, the proof consists of 3 steps. So basically, we're gonna show 2 inequalities based upon our preconditions, 2 preconditions. And then we're gonna connect these 2 inequalities, leverage the Cauchy-Schwarz inequality, and then get our bound. Okay. The first step, we want to show a claim that after making T mistakes, in other words, after making T model updates, we have the dot product between your U vector and WT is no less than T times gamma. This is the very first claim we want to show. Right? And how do we show this? We're gonna use a induction method. Right? So what's the induction? What's the framework of doing induction? Yes. Yeah, exactly, right? Let's just memorize, like let's just try to recall what we have done like in our through our junior school and high school, right? So induction consists of 2 steps, right? First, you need to show like the base case, the very beginning, this is true, right? Second, let us assume at every step T, suppose your conclusion is correct, then you can extend it to the step T plus 1. Right? If you can show 2 steps altogether, you can extrapolate your conclusion to every possible steps, and then it shows your result. Right? This is induction. Okay. So let us first assume, okay, at step T, here step T means like you have made T mistakes, right? This is correct. Now let's see whether we can extrapolate the same conclusion at T plus 1. Okay. So we're looking to the dot product between U and the T plus 1, right? That means after making T plus 1 mistakes, right? Because T plus 1 is obtained from a mistake. So we're gonna follow our updating rule, right? Remember, updating rule is WT plus 1. Oh, it's here, right? Is got by adding WT by YI XI, right? So if we look into the U transpose with WT plus 1, it essentially can be decomposed as U transpose WT plus the dot product between this guy, the addition part with WT, right? With XI, which is YI U transpose XI, right? And according to our second condition, because U is a separating hyperplane, right? It has a margin gamma. So this guy actually represents the distance between xi and the separating hyperplane determined by U, right? So this guy must be a no less than gamma, right? That's our second condition, right? Here. We just leverage this result, right? So we know that U transpose that WT plus 1 will be bigger than or equal to U transpose WT plus gamma, right? And from our pre-assumption, we're assuming at this conclusion is correct at step T. That means we're assuming this one is bigger than or equal to T plus gamma, right? You merge them together, you get at T plus 1, U transpose WT plus 1 is no less than T plus 1 times gamma, right? So it's kind of consistent with the claim, right? Does it make sense? Right? So in this step, we show, okay, assuming your claim is correct at step T, you can extrapolate to T plus 1. You finish one step of induction, right? Right? And then the remaining is that you just show at initial step, your claim is correct as well. And initial step is T is a W0, right? So before you make any mistake, your W0 is 0. Because we initialize all the weight vector, we initialize the weight vector to be 0 before training. Right? At T is 0, when W0 is 0, then U transpose W0 is 0. And T is 0, and right hand side is 0 as well. So that means at the beginning, the claim is correct as well. Then combine the previous step, you can see we can extrapolate from step 0 to step 1, and then from 1 to 2, from 2 to 3, and so on. And we have finished the proof that after making any T mistakes, we have U transpose WT is no less than T times gamma. Any question? Again, this is kind of like a straightforward application of the induction, right? If you feel uncomfortable or feel you didn't catch up, that's fine. Like after class, please look at the slides and do it by yourself. It's not hard. It's just to apply the standard induction framework. Okay, so the second claim. The second claim is after T mistakes, my square norm of WT will be upper bounded by T times R squared. Remember, R is the upper bound of the norm for each feature vector, right? So here we claim that, okay, after making T mistakes, the square norm of your weight vector will be no bigger than T times R squared, right? And the proof still is induction, right? So let's assume, okay, at step T, this is correct, whether we can extrapolate the same conclusion to T plus 1. Right? To see this, right, we'll look into the square norm of WT plus 1, and WT plus 1, according to the update rule, is actually WT plus YI XI, right? And if you expand the square norm, you got three terms, right? The square norm of WT, the square norm of XI, and this cross term. So here's the key observations, right? So first, this guy, from our precondition, we know the norm of each feature vector xi will be upper bounded by R. So that means this term is upper bounded by, R squared, right? And this guy actually is negative. Why? Why is this negative? Yeah. Because WT plus 1 is updated only when you make a mistake, right? So when you make a mistake, that means your prediction is wrong on xi. Then this product must be negative. Right? Otherwise, you won't update, right? You won't get WT plus 1. You have to wait. You have to wait until you make a mistake on the next example, right? So now that you make a mistake, you get that WT plus 1. That means, okay, you're going to incorrectly classify xi. That's why this product will be negative. Right? So that means this right-hand side can be further upper bounded by WT square norm plus 0 plus R square, right? And from our induction assumption, this guy is less than or equal to TR square plus this guy, it will become a T plus 1 R square, right? That's how you extrapolate to the step T plus 1, right? And then what do we, the remaining is to show the initial case, right? The initial case again is step 0, T is 0, and W0 will be 0, and T is 0, 0 less than or equal to 0. So initial step is correct, and then the following our induction steps, it can extrapolate to arbitrary steps. Okay. Then we have proved the second claim. Any question? Okay, so now look at what we have so far, right? After T mistakes, we know the dot product between U and WT is no less than T times gamma, right? And after T mistakes, we have the square norm of WT less than or equal to T times R squared. Right? So now we want to connect these two inequalities together so that we can solve it and we can get upper bound about T. T is the number of mistakes, right? So from the second result, right, if we just revert the direction of the inequality and take the square root, we have R times square root T is no less than the norm of WT, right? You just take square root on both sides and just take the reverse, take the inverse, not inverse, just revert to this inequality, right? And then one key step is that the norm of WT is no less than the dot product between U and WT. This follows from the Cauchy-Schwarz inequality. So what is Cauchy-Schwarz inequality? So it comes from like a definition of cosine function, right? So in arbitrary, we know that in arbitrary dimensional space, right? If we want to look at the angle between two vectors, right? Like U and W, right? We know that this cosine theta is what? Is the dot product between the two vectors and then divided by the product of their norms. Right? This is just a formula. I bet everyone has seen this before, right? Maybe a long time ago. But this is just the definition of cosine of the angle between two vectors in arbitrary space. And here, we know U is a unit vector. So U is 1, right? So you have this guy to be 1. You can just erase it. And we know cosine theta must be less than or equal to 1, right? And now you just move WT, the norm of WT to the right-hand side. You got your result. This is also called Cauchy-Schwarz inequality. Okay. Again, if you feel uncomfortable or you didn't feel like you get it point or catch up, it just doesn't matter. Just look at the slides after the class. You get it like in 5 minutes, right? And then we connect In this way, by applying this Cauchy-Schwarz inequality, we connect the norm of WT with W transpose WT now to the first assertion or claim, right? So we just apply it again, right? We know that U transpose WT is no less than T times gamma is our first conclusion. This is our second conclusion. We'll connect them together. We just need to solve R times square root T is no less than or equal to T times gamma, right? This is an inequality regarding T, and it's easy to solve. We know that the number of mistakes T will always be less than or equal to R squared over gamma squared. Then we get our results. Okay? And in this way, we bound the total number of mistakes. Any question? So again, to summarize, this proof consists of 3 steps, right? Based on the preconditions, we have a we can show that after T mistakes, the dot product between the unit vector U and WT is no less than T times gamma. Okay. And second, we can show that after T mistakes, the square norm of the weight vector is no bigger than T times R squared. And then you just connect these two inequalities through Cauchy-Schwarz inequality. Then you solve the whole inequality according to T, you got this upper bound. It's a little bit tedious, but every component is not, I mean, it's relatively straightforward. You just need to piece them together. Okay. So now let us look at the whole theorem again, right? So let us have like M training examples, and every training example, I, the feature vector, its norm is upper bounded by R, and the label is either 1, -1, or 1. And we're assuming that we have a separating hyperplane whose bit vector is a unit vector, and so the margin is gamma. Then Mystic bound theorem tells that perceptron algorithm will always converge. No matter orders you fit an algorithm, the training examples, right? The number of total mistakes the perceptron algorithm make is at most R over gamma take square. There's many, right? So what's some kind of like geometry intuition for this, right? So suppose this is our data set. And remember, we're talking about the cases where you have a linear separable data set, right? So this is a positive and this is negative, right? So first, we can draw a ball which encapsulates all the training examples, meaning that the length of each feature vector will not exceed this radius R, right? And then we can find out a separating hyperplane whose margin is gamma. Then our claim is that you use this data set to train our perception, right? You run a perception in whichever order of sequence of the training example, right? The total number of mistakes you're gonna make will no bigger than R squared over gamma squared. So will be no bigger than this ratio between the radius R and this margin gamma and take square. So that's the conclusion. Any question? How we exactly get R? That one is pretty simple, right? You just look at the norm of each feature vector, right? You pick up the maximum. Okay. The only thing that might feel unclear, you might feel unclear, is gamma, right? Actually, this applies to any gamma. So as long as you can find out a separating hyperplane whose margin is positive, you can use it as gamma, and you get some upper bound of the mistakes. This applies to any separating hyperplane with non-zero margin. Because obviously, that relates like the biggest upper bound, right? The biggest upper bound corresponds to the separating hyperplane who has the smallest margin, right? But they have the smallest upper bound, right? Smallest upper bound corresponds to the separate plane, which corresponds to the margin of the whole data set, right? The margin of the whole data set means that, okay, you're going to find out a separating hyperplane whose margin with respect to this data set is the largest among all possible separating hyperplanes. Okay? Then you can the minimum upper bound of the number of mistakes for your perception. Okay, yeah, that's a very good question. So this is just to characterize the behavior perception, because in practice you will never know. Like, because in practice you will never, your goal is to find out such a hyperplane, right? Separating hyperplane, rather than using some existing hyperplane to bound the number of mistakes. So this theorem just tell you if your data set is linear separable, then after a finite number of mistakes, you're going to converge. Right? As to how much quantity the number of mistakes you're going to have, right? It gives you some upper bound, but it doesn't mean any practical value, because in practice, if you do find a separating hyperplane, then why do you run a perception algorithm, right? So there's no practical sense. It just to give you some like theoretical guarantees. So that's why like it's not practical at all. It's just to give you some guarantees, like, okay, don't worry, you have a linear separable data set, you always converge, and the number of mistakes you make at most won't be too many. It's just the radius of the ball, which cover the entire data set by some margin, by the margin for some separating hyperplanes. That's it. Very good question. Any other question? Okay. So by leveraging this perception mystic bound, like at least in some like simple toy cases, we can estimate the upper bound for perceptual learning. To strengthen our understanding about the theorem, I think next lecture we're going to manually do some kind of estimate. Again, this doesn't have any practical value. It's just to strengthen our understanding about this theorem. But I guess okay, let's stop here today a little bit earlier, and so we have like enough time and context to do some practice next lecture. Okay, see you on Thursday.